All right, welcome back. Let's prove Lemma 3.7 here. So just to save a little bit of writing, let's use some notation. TCO is my abbreviation for the column operation that transforms the identity to E. You know, every elementary matrix can be written as the result of doing some column operation to the identity to get that. Now, we know that that's also the operation that turns A into A times E. And we know it's the same one from Theorem 2.16. Now, let's think about what the three possibilities for the column operation are. One thing is that the column operation might be a swap, swapping two columns. In that case, we know from the antisymmetry theorem that the determinant of AE is going to be equal to -1 times the determinant of A, because AE is the result of swapping two columns of A by Theorem 2.16. And in that case, we also know that that same swap turns the identity matrix into E. So what is the determinant of E going to be? Well, for the same reason, the determinant of E is going to be -1 times the determinant of the identity matrix, which we know is 1. And in this case, the theorem is true because the determinant of E is the result of doing the same thing to the identity, so the determinant of E is also -1. So that works. Now, the same idea holds for the other operations, so let's go through that really quick. So if it's a scaling operation, by scaling linearity, we know the determinant of AE, the result of scaling that column, is K times the determinant of A. Now, the same principle applies to the columns of the identity matrix. If we scale a column of the identity matrix, the resulting determinant is K times that determinant of the identity matrix, which is just 1, so we still get just K here. Same thing if it's multiplicity. It's even easier. Multiplicity doesn't change the determinant at all, either of A, E, or of just E itself. So the determinant of AE is 1 times the determinant of A because it's unchanged, and that's the determinant of E. So either way, the determinant of AE is equal to the determinant of E times the determinant of A. And that's what the theorem says. So yeah, this result might feel, I don't know, maybe a little unsatisfying. This proof feels like there's not really much going on maybe, but it points out something we're going to need for the proof of the next theorem, 3.8, which is actually pretty deep. And it's nice and simple and it's elegant, but it hides a lot of complexity. It almost feels kind of magical because the columns of A, B are linear combinations of the columns of A using the entries and B as weights. If you try to think about this in terms of volume of parallelepipeds and parallelograms, it's really hard to picture what the columns of A, B are going to look like and what the volume of that parallelepiped is. And what does it have to do with the volumes of these parallelepipeds? Well, we're going to prove it here. And the trick is going to be using this lemma 3.7. Now, there's two possibilities, and we're going to have to sort of prove them separately. One is that if B is not invertible, it turns out that that implies that AB is not invertible. And why is that? You're going to prove that in an exercise in 2.4, or you probably already have at this point. So based on this fact, when B is not invertible, that means the determinant of A times the determinant of B is the determinant of A times 0, because we know the determinant of a non-invertible matrix is 0, which was theorem 3.5 in section 3.1. And anything times 0 is 0. And if AB is not invertible, same thing. That implies that the determinant of AB is 0. And of course, 0 equals 0. So they're both equal to 0. So the theorem works if B is not invertible. What if B is invertible? Well, then by the invertible matrix theorem, we know that it is row equivalent to the identity. Right? If one of these things is true, the rest must be true. And if B is row equivalent to the identity matrix, all of those row operations that transform B to the identity matrix can be reversed. So you can transform the identity matrix back into B using these row operations. And we also know that row operations have elementary matrices that you could multiply by the identity in the right order to get B, to do those row operations. So in other words, we can say that B is the result of first doing the row operation 1 to the identity. And we know that multiplying on the left of the identity like this does that row operation to the identity. This is theorem 2.17 that says that. And multiplying on the left of that does the next row operation, and so on until you have transformed I all the way back into B. And of course, we don't even need to write the I here. We could just write this as En times yada 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 up to E2 times E1. So now let's think about the determinant of A times B, but replacing B with this product of elementary matrices, because then we're going to be able to use lemma 3.7 here. Now, how can we use lemma 3.7? Well, lemma 3.7 says the determinant of any square matrix times an elementary matrix. Well, all of this stuff is a matrix, and E1 is an elementary matrix. So we can apply lemma 3.7 to that and say we're going to do the determinant of the matrix on the left here, and we get the same thing when we multiply that by the determinant of this elementary matrix E1. And then we can repeat this process again to get the determinant of E2 off of this. This time E2 is an elementary matrix, and then everything else, E3 all the way back up to A, is another matrix. And we can repeat this process using Lemma 3.7 a bunch of times until we have all of these elementary matrices in their own determinants, like so. But how does that get us back to the determinant of B? Well, we can actually use Lemma 3.7 to combine these together again, because Lemma 3.7, you could also go backwards, right? If you have the determinants of two of these matrices and the one on the right is elementary, then you can combine them again. And we're going to do that with these two here. Combine that there. And then also repeat this process n minus 1 more times until we have the determinant of A times the determinant of all the elementary matrices combined. And that matrix inside there is B. Just resubstituting it back. And that proves that theorem. All right, next we'll do a similar trick to prove another theorem about the determinants of transposes.